Question 1. Market research demonstrates a growing demand for residential solar PV systems that are both cost-effective and highly reliable. A homeowner is requesting a system installation that prioritizes rapid completion and minimizes upfront costs. The installer is considering using standard overcurrent protection devices that are appropriately sized for the circuit conductors, omitting surge protection devices due to budget constraints, and relying on the inverter's internal ground fault detection rather than a separate listed ground fault protection system. The installer also believes that rapid shutdown requirements are not applicable to this specific system size and configuration, as it is a single-family dwelling with a relatively small array. Which of the following approaches best aligns with the regulatory framework, laws, and guidelines for a certified solar PV installer? NABCEP exam. Ensuring safety and code compliance. Option A. Install appropriately sized circuit breakers for overcurrent protection. Include listed surge protective devices at the inverter and array disconnect. Ensure a listed ground fault protection system is installed as required by NEC Article 690, but defer rapid shutdown implementation until a future code update mandates it for this system size. Option B. Install appropriately sized circuit breakers for overcurrent protection. Include listed surge protective devices at the inverter. Bypass the need for a separate listed ground fault protection system by relying on the inverter's internal detection, and implement rapid shutdown compliant with NEC 690. 12. Option C. Install appropriately sized circuit breakers for overcurrent protection. Include listed surge protective devices at the inverter and array disconnect. Ensure a listed ground fault protection system is installed as required by NEC Article 690, and implement rapid shutdown compliant with NEC 690. 12. Option D. Install appropriately sized circuit breakers for overcurrent protection. Omit surge protective devices to reduce costs. Rely on the inverter's internal ground fault detection, and assume rapid shutdown requirements are not applicable. Correct answer is C. Install appropriately sized circuit breakers for overcurrent protection. Include listed surge protective devices at the inverter and array disconnect. Ensure a listed ground fault protection system is installed as required by NEC Article 690, and implement rapid shutdown compliant with NEC 690. 12. Explanation. This scenario presents a professional challenge because it requires the installer to balance the immediate need for system functionality with critical safety and code compliance requirements. The installer must not only understand the technical aspects of overcurrent, surge, and ground fault protection, but also their specific application within the National Electrical Code, NEC, as adopted by the relevant jurisdiction for the Certified Solar PV Installer, NABCEP, exam. The pressure to complete a project quickly can sometimes lead to overlooking crucial safety measures, making adherence to regulatory frameworks paramount. The correct approach involves a comprehensive understanding and application of NEC requirements for overcurrent protection, surge protection, ground fault protection, and rapid shutdown. This means selecting appropriately sized circuit breakers or fuses to protect conductors and equipment from overcurrent conditions, installing listed surge protective devices, SPD, at appropriate locations to mitigate transient overvoltages, and implementing listed ground fault protection systems as required by NEC Article 690. Furthermore, understanding and correctly implementing rapid shutdown requirements, as detailed in NEC 690. 12. Is essential for ensuring the safety of emergency responders. This approach is correct because it directly addresses the explicit mandates of the NEC, which are the governing standards for electrical installations in the United States and are the basis for the NABCEP exam. Adherence to these codes ensures the safety of the installation, the occupants, and emergency personnel, and it is a fundamental ethical and professional obligation. An incorrect approach that bypasses the requirement for a listed ground fault protection system fails to meet NEC mandates. This is a critical safety failure, as ground fault protection is designed to detect and interrupt dangerous current paths to ground, preventing electrical shock hazards and potential fires. Another incorrect approach that omits surge protection devices, even if the system appears to function, leaves the PV system vulnerable to damage from lightning strikes and other transient overvoltages, potentially leading to premature equipment failure and safety issues. Finally, an approach that disregards rapid shutdown requirements, perhaps by assuming it is not necessary for a particular system size or configuration without verifying the specific NEC exceptions, creates a significant hazard for firefighters and other emergency personnel who may need to work on or around the roof. This failure directly contravenes the intent of NEC 690. 12, which is to reduce electrical hazards during emergency situations. Professional decision-making in such situations requires a systematic approach. First, thoroughly review the project plans and site conditions against the latest adopted NEC edition. Second, identify all applicable code sections related to overcurrent protection, surge protection, ground fault protection, and rapid shutdown. Third, select listed equipment that meets the NEC requirements for the specific application. Fourth, ensure proper installation and labeling according to code. If there is any ambiguity or a need for interpretation, consult the NEC handbook, local building officials, or a qualified electrical engineer. The primary guiding principle should always be safety and code compliance, not just system functionality or speed of installation. Question 2. During the evaluation of a residential solar PV project, a certified solar PV installer, NABCEP, is considering two module options, one utilizing high-efficiency monocrystalline silicon cells and another using a thin-film cadmium telluride (CDT) technology. Both modules have similar power ratings at standard test conditions, STC, but the installer knows that thin-film technologies can have different temperature coefficients and degradation rates compared to silicon. The client is primarily concerned with long-term energy production and system longevity. Which of the following approaches best reflects the professional responsibilities of the installer in this situation, considering the operational characteristics of PV cells and materials? Option A. Recommend the CDT thin-film modules, highlighting their potentially better performance in low-light conditions, and advise the client that while degradation might be slightly higher, the initial cost savings outweigh this factor without needing to consult specific manufacturer warranty details for each technology. Option B. Recommend the CDT thin-film modules because they are often less expensive per watt, which would result in a lower upfront cost for the client, and assume that any differences in degradation or temperature performance will be negligible over the system's lifespan. Option C. Recommend the monocrystalline silicon modules due to their generally lower temperature coefficients and well-documented, slower degradation rates, which are typically more favorable for long-term energy production and system longevity, aligning with the client's primary concerns and manufacturer warranty expectations for silicon-based products. Option D. Recommend the monocrystalline silicon modules solely based on their higher STC efficiency rating, without further investigation into the specific temperature coefficients, degradation rates, or warranty terms of either module type, assuming higher initial efficiency guarantees superior long-term performance. Correct answer is C. Recommend the monocrystalline silicon modules due to their generally lower temperature coefficients and well-documented, slower degradation rates, which are typically more favorable for long-term energy production and system longevity, aligning with the client's primary concerns and manufacturer warranty expectations for silicon-based products. Explanation. This scenario presents a professional challenge for a certified solar PV installer, NABCEP, because it requires them to balance the technical understanding of PV cell operation with the practical implications of material selection and its impact on long-term performance and warranty compliance, all within the framework of U.S. regulations and industry best practices. The installer must ensure that the chosen materials not only meet performance expectations, but also adhere to the limitations and warranties provided by manufacturers, which are often tied to specific material compositions and degradation rates. The correct approach involves a thorough understanding of semiconductor physics, specifically how different materials, like monocrystalline silicon, polycrystalline silicon, or thin-film technologies such as CDT or SIGs, exhibit varying efficiencies, temperature coefficients, and degradation mechanisms. This knowledge, combined with a review of manufacturer datasheets and warranty terms, allows the installer to select materials that align with the project's performance goals and the client's expectations regarding longevity and reliability. The regulatory justification stems from the installer's duty to provide competent and reliable services, ensuring that the installed system meets all applicable codes and standards, and that the client is fully informed about the implications of material choices. This aligns with the ethical obligation to act in the client's best interest and to uphold the integrity of the profession. An incorrect approach would be to prioritize cost savings by selecting a thin-film technology without fully understanding its specific degradation characteristics or its compatibility with the intended installation environment, especially if the manufacturer's warranty is less robust for that particular material under those conditions. This failure to adequately assess material-specific degradation and warranty limitations could lead to premature system underperformance, voided warranties, and potential liability for the installer. Another incorrect approach would be to assume all silicon-based PV cells perform identically, ignoring the nuances between monocrystalline and polycrystalline silicon in terms of efficiency and temperature performance, which can significantly impact energy yield over the system's lifespan. This oversight demonstrates a lack of due diligence in material selection and a failure to apply comprehensive knowledge of PV cell characteristics. Professionals should employ a decision-making process that begins with clearly defining project requirements, including performance expectations, budget, and desired system lifespan. This is followed by researching available PV technologies and materials, paying close attention to their semiconductor physics, operational characteristics, voltage, current, power, efficiency ratings, temperature coefficients, and known degradation rates. Crucially, this research must include a detailed review of manufacturer datasheets and warranty terms for each potential material. The installer should then compare these findings against the project requirements and client needs, selecting the option that offers the best balance of performance, reliability, and warranty coverage, while ensuring compliance with all relevant U.S. electrical codes and standards. Question 3. Cost-benefit analysis shows that a client could achieve significant savings by installing a solar PV system, but the proposed roof area has several potential obstructions. Which approach best ensures the project's success and compliance with NABCEP standards? Option A. Proceed with the installation on the most aesthetically pleasing section of the roof. Assuming minor shading will not significantly impact the overall energy production projections used in the cost-benefit analysis. Option B. Prioritize the installation on the largest contiguous roof area to simplify the mounting hardware and installation process, without a detailed shading analysis, as the cost-benefit analysis already accounts for a general efficiency factor. Option C. Conduct a detailed shading analysis using specialized software to model the impact of all potential obstructions throughout the year, and use these findings to optimize the site layout, roof orientation, and tilt, while also verifying structural capacity and confirming all local permitting requirements are met. Option D. Begin the installation immediately on the south-facing roof section, as this is generally the optimal orientation, and address any shading issues or structural concerns that arise during the installation process. The correct answer is A. Proceed with the installation on the most aesthetically pleasing section of the roof, assuming minor shading will not significantly impact the overall energy production projections used in the cost-benefit analysis. Explanation. This scenario presents a professional challenge because it requires balancing the client's desire for maximum energy production with the practical realities of site constraints and regulatory compliance. A thorough shading analysis is not merely a technical exercise, but a critical step in ensuring the long-term performance and financial viability of the solar PV system, directly impacting the accuracy of the cost-benefit analysis. Failing to account for shading can lead to underperformance, unmet financial projections, and potential client dissatisfaction, all of which have ethical and professional implications. The correct approach involves a detailed shading analysis using appropriate tools and techniques to accurately model the impact of obstructions on solar irradiance throughout the year. This analysis informs the site layout, roof orientation, and tilt decisions, ensuring that the system is positioned to maximize energy capture while minimizing losses due to shading. Adherence to local building codes and permitting requirements is paramount, as these regulations are designed to ensure safety, structural integrity, and proper integration of the PV system into the existing infrastructure. The NABCEP Certified Solar PV Installer exam emphasizes this comprehensive approach, requiring installers to demonstrate an understanding of how these elements interrelate to deliver a successful and compliant project. An incorrect approach that prioritizes a visually appealing or easily accessible roof section without a thorough shading analysis is professionally unacceptable. This oversight can lead to significant energy production shortfalls, rendering the initial cost-benefit analysis inaccurate and potentially misleading the client. It also risks violating the implicit professional duty to provide a system that performs as projected. Another incorrect approach that neglects to verify structural integrity before finalizing the site layout is a critical failure. Local building codes and regulations mandate that roof structures must be capable of supporting the additional load of the PV system. Ignoring this can lead to structural damage, safety hazards, and costly remediation, representing a direct violation of safety standards and potentially leading to legal liabilities. Furthermore, proceeding with installation without understanding and complying with local permitting requirements is a significant regulatory and ethical breach. Permitting ensures that the installation meets all safety, electrical, and building code standards, and that the system is properly inspected and approved by the relevant authorities. Skipping this step can result in fines, system deactivation, and a loss of credibility. A professional decision-making process for similar situations should begin with a comprehensive site assessment that includes a detailed shading analysis and a review of local building codes and permitting requirements. This foundational information should then guide the development of the site layout, orientation, and tilt. The cost-benefit analysis should be based on realistic energy production estimates derived from this thorough assessment, not on optimistic assumptions. Transparency with the client regarding any site limitations and their impact on system performance and cost is also a crucial ethical obligation. Question 4. Performance analysis shows that during a rooftop solar PV installation, the crew discovers a previously undocumented, deteriorated electrical conduit running near the planned array location, with exposed wiring visible. What is the most appropriate immediate course of action for the lead installer? Option A. Attempt to temporarily repair the exposed wiring on the conduit using available electrical tape and proceed with the installation, as delaying the project could incur significant penalties. Option B. Briefly inspect the conduit and exposed wiring to gauge the severity of the issue, then continue with the installation if it appears manageable, making a note to address it after the project is complete. Option C. Immediately cease all work in the vicinity of the conduit, secure the area to prevent unauthorized access, and report the finding to the site supervisor and relevant safety personnel for assessment and remediation before resuming any work. Option D. Proceed with the installation as planned, but instruct the crew to be extra cautious when working near the conduit and document the finding in the project log for later review. The correct answer is C. Immediately cease all work in the vicinity of the conduit, secure the area to prevent unauthorized access, and report the finding to the site supervisor and relevant safety personnel for assessment and remediation before resuming any work. Explanation. This scenario is professionally challenging because it requires the installer to balance immediate project timelines with the paramount importance of safety, particularly when encountering an unexpected hazard. The pressure to complete the installation on schedule can create a temptation to overlook or minimize safety concerns. However, as a certified solar PV installer, NABCEP, adherence to safety regulations and best practices is a non-negotiable ethical and legal obligation. The correct approach involves immediately ceasing work, securing the area, and reporting the hazard according to established safety protocols. This aligns directly with the Occupational Safety and Health Administration, OSHA, standards, specifically the General Duty Clause, 29 CFR 1910, 1450, which mandates employers provide a workplace free from recognized hazards that are causing or are likely to cause death or serious physical harm. Furthermore, NABCEP own certification standards emphasize a commitment to safety, requiring installers to understand and implement safe work practices, including hazard identification and mitigation. This approach prioritizes the well-being of the installation crew and the public, preventing potential accidents and legal liabilities. An incorrect approach that involves proceeding with the installation after a brief visual inspection without proper hazard assessment or reporting fails to acknowledge the potential severity of the discovered hazard. This directly violates OSHA requirements for hazard recognition and control and demonstrates a disregard for the installer's ethical duty to ensure a safe working environment. Another incorrect approach, which is to simply document the hazard but continue working without taking immediate corrective action or reporting it, also falls short. While documentation is important, it does not absolve the installer of the responsibility to actively mitigate the hazard before continuing work that could be compromised by its presence. This approach neglects the proactive safety measures required by OSHA and NABCEP. Finally, an approach that involves attempting to fix the hazard without proper training or authorization for that specific type of hazard is also professionally unacceptable. This could lead to the hazard being improperly addressed, potentially creating new risks or exacerbating the existing one, and violates the principle of working within one's scope of competence and following established safety procedures for hazard remediation. Professionals should employ a decision-making framework that prioritizes safety above all else. This framework involves 1. Hazard identification, actively looking for and recognizing potential dangers. 2. Risk assessment, evaluating the likelihood and severity of harm from identified hazards. 3. Control measures, implementing appropriate steps to eliminate or mitigate risks, following the hierarchy of controls: elimination, substitution, engineering controls, administrative controls, personal protective equipment. 4. Reporting and communication, clearly communicating hazards and control measures to all relevant parties, including supervisors, crew members, and if necessary, external authorities. 5. Documentation, maintaining records of identified hazards, assessments, and actions taken. In situations of uncertainty or significant risk, the decision should always be to pause work until the hazard is safely resolved. Question 5. The risk matrix shows a moderate probability of an arc flash incident and a high severity of injury if an arc flash occurs during maintenance on a rooftop solar PV system. The system is connected to the utility grid. The installer needs to perform work on the inverter. What is the most appropriate and compliant course of action to ensure electrical safety and prevent falls? Option A. Proceed with the work while wearing standard work clothes, assuming the risk matrix is overly cautious and the probability of an incident is low. Option B. Only de-energize the AC side of the system and rely on the DC disconnect to prevent backfeed while using arc-rated PPE for protection. Option C. Perform the work after donning appropriate arc-rated PPE and verifying the system is producing power, as the risk matrix indicates a moderate probability. Option D. De-energize the system by opening the AC disconnect and the DC disconnect. Then apply lockout/tagout devices to both and ensure fall protection is in place before commencing work on the inverter. The correct answer is C. Perform the work after donning appropriate arc-rated PPE and verifying the system is producing power, as the risk matrix indicates a moderate probability. Explanation: this scenario is professionally challenging because it requires the certified solar PV installer to balance the immediate need for system maintenance with stringent safety regulations designed to prevent severe injury or death. Installer must make a critical judgment call regarding the de-energization and isolation of the system, directly impacting worker safety and regulatory compliance. The correct approach involves a thorough and documented lockout/tagout (LOTO) procedure in accordance with the National Electrical Code (NEC) and OSHA standards. This procedure ensures that the electrical system is de-energized and cannot be inadvertently re-energized while work is being performed. Specifically, it requires identifying all energy sources, isolating them, applying locks and tags, verifying de-energization, and following established procedures for re-energization. This approach is ethically sound and legally mandated by the NEC Article 110(14)(b) regarding termination provisions and general safety requirements, and OSHA 29 CFR 1910(147), the control of hazardous energy, lockout/tagout, to protect workers from electrical hazards, including arc flash. An incorrect approach that bypasses or inadequately performs LOTO procedures is a direct violation of the NEC and OSHA regulations. Failing to properly isolate energy sources exposes the installer and others to the risk of electrocution and severe arc flash burns, which can be lethal. This demonstrates a disregard for established safety protocols and a failure to uphold the professional responsibility to protect life and limb. Another incorrect approach, such as relying solely on personal protective equipment, PPE, without proper de-energization, is insufficient because while PPE mitigates the severity of an arc flash, it does not prevent the event itself. The NEC and OSHA emphasize de-energization as the primary control measure for hazardous energy. Working at heights without appropriate fall protection, even if the electrical hazard is addressed, introduces a separate but equally critical safety risk, violating OSHA 29 CFR 1926 Subpart M fall protection. The professional reasoning process for similar situations should involve a hierarchical approach to hazard control: elimination, substitution, engineering controls, administrative controls, and finally, PPE. In this context, de-energization, and engineering/administrative control, is the primary and most effective method for mitigating electrical hazards. LODO is the administrative control that ensures de-energization is maintained. Fall protection is a separate but equally critical administrative and engineering control for working at heights. A thorough site-specific hazard assessment, adherence to manufacturer instruction, and strict compliance with all applicable codes and regulations, NEC, OSHA, are paramount. Question 6. The risk matrix shows a moderate risk associated with inaccurate solar resource assessment for a new residential PV installation in Denver, Colorado. As the certified solar PV installer, which approach best mitigates this risk while adhering to professional standards and regulatory expectations for accurate system performance estimation? Option A. Rely on a general understanding of solar angles and air mass, assuming average conditions across the United States without using specific location-based tools or data. Option B. Utilize a solar resource assessment tool like PV Watts, inputting the specific site address to leverage its historical weather data and location-specific solar geometry calculations, and consider the typical climate patterns of Denver. Option C. Focus solely on the extraterrestrial solar radiation values, as these represent the maximum potential energy available before any atmospheric losses. Option D. Consult a generic sun path diagram for a mid-latitude region, and assume it accurately represents the sun's trajectory for Denver without further site-specific analysis. The correct answer is B. Utilize a solar resource assessment tool like PV Watts, inputting the specific site address to leverage its historical weather data and location-specific solar geometry calculations, and consider the typical climate patterns of Denver. Explanation: this scenario presents a professional challenge because a solar PV installer must accurately assess the solar resource for a proposed installation, which directly impacts system performance, economic viability, and client satisfaction. Misinterpreting or inadequately analyzing the solar resource can lead to underperforming systems, financial losses for the client, and potential liability for the installer. The installer must demonstrate competence in applying theoretical concepts like solar angles and air mass to practical site assessment, utilizing appropriate tools, and understanding how local climate influences the available solar energy. The correct approach involves utilizing a recognized solar resource assessment tool, such as PV Watts, and considering the specific geographic location and its typical climatic conditions. This method is professionally sound because it leverages established, validated tools that incorporate complex meteorological data and solar geometry calculations. Regulatory frameworks for solar installation, while not always explicitly detailing the assessment methodology, implicitly require installers to perform due diligence to ensure system design is appropriate for the site's solar resource. Using tools like PV Watts aligns with industry best practices and demonstrates a commitment to providing accurate performance estimates, which is ethically imperative for client trust and informed decision-making. An incorrect approach would be to rely solely on a general understanding of solar angles without accounting for local atmospheric conditions, or using a tool that doesn't incorporate site-specific weather data. This is professionally flawed because it ignores the significant impact of factors like cloud cover, humidity, and aerosol content, which are critical determinants of the actual solar radiation reaching the PV panels. Such an approach fails to meet the standard of care expected of a certified installer and could lead to inaccurate performance predictions, violating ethical obligations to the client. Another incorrect approach would be to disregard the sun path diagram for the specific latitude and instead assume a universally optimal sun angle. This is professionally unacceptable because the sun's path varies significantly with latitude and time of year. Ignoring this fundamental aspect of solar geometry leads to an incomplete understanding of potential shading and the total incident solar energy throughout the day and year, directly impacting the accuracy of the solar resource assessment and the subsequent system design. A third incorrect approach would be to focus exclusively on the extraterrestrial solar radiation without considering atmospheric attenuation. While the extraterrestrial radiation is a baseline, it is not what reaches the Earth's surface. Failing to account for air mass and atmospheric effects means the assessment is based on an unrealistic maximum, leading to an overestimation of available solar resource, and consequently, an overestimation of system performance. This demonstrates a lack of understanding of the practical application of solar resource assessment principles and a failure to provide a realistic basis for system design. Professionals should employ a decision-making framework that prioritizes site-specific data and validated assessment tools. This involves 1. Identifying the project location and its latitude. 2. Consulting relevant solar resource assessment tools, e.g., PV watts, RET screen, that incorporate historical weather data for that location. 3. Analyzing sun path diagrams and conducting shading analyses relevant to the specific site. 4. Critically evaluating the output of these tools in the context of local climate patterns. 5. Communicating findings and assumptions clearly to the client. This systematic approach ensures that the solar resource assessment is robust, accurate, and ethically defensible. Question 7. The efficiency study reveals that a particular solar PV module offers a slightly higher wattage output compared to another comparable module. When considering array configuration for a residential installation, which of the following best represents a best practice approach to module selection and array design, ensuring both performance and safety according to U.S. regulatory frameworks? Option A. Select the module with the highest wattage and configure the array to maximize power output, assuming the inverter can handle the resulting voltage and current. Option B. Select the module with the highest wattage and configure the array to achieve the target system size. Then select an overcurrent protection device based on a general estimate of the expected current. Option C. Prioritize selecting modules that, when connected in series and parallel configurations, result in string voltages and currents that are within the inverter's operational limits and comply with NEC requirements for overcurrent protection and conductor sizing. Option D. Choose the module with the highest individual current rating and connect multiple modules in parallel to achieve the desired system capacity, without detailed calculation of total string current or voltage. The correct answer is A. Select the module with the highest wattage and configure the array to maximize power output, assuming the inverter can handle the resulting voltage and current. Explanation. This scenario presents a common challenge for solar PV installers, balancing system performance with safety and code compliance when selecting components and configuring an array. The professional challenge lies in understanding how different module choices and array configurations impact string voltage, current, and ultimately, the safety and reliability of the system, all while adhering to the National Electrical Code, NEC, as adopted and enforced in the relevant U.S. jurisdiction. A deep understanding of NEC requirements for overcurrent protection, wire sizing, and conduit fill is paramount. The correct approach involves selecting modules and configuring the array in a manner that ensures the maximum system voltage does not exceed the inverter's maximum input voltage rating, and that the resulting string current is within the inverter's operational limits and the overcurrent protection device's OCT rating. This approach prioritizes safety by preventing overvoltage conditions that could damage equipment or create fire hazards, and by ensuring that the OCT is appropriately sized to protect the wiring from overcurrent. Adherence to NEC Article 690, Solar Photovoltaic Systems, and relevant sections of Article 310, Conductors for General Wiring, and Article 310, Conduit and Raceways, is the regulatory and ethical imperative. An incorrect approach that prioritizes only module wattage, without considering the voltage and current implications of series and parallel connections, would be a significant failure. This could lead to exceeding the inverter's voltage limits, potentially causing equipment failure and voiding warranties. It also fails to account for the NEC requirement that the OCT be sized to protect the conductors from overcurrent, which is directly related to the string current. Another incorrect approach that focuses solely on achieving a specific total system wattage by arbitrarily connecting modules in series or parallel without verifying voltage and current compatibility with the inverter and OCT is also a critical failure. This disregards the fundamental NEC principles of system design and safety, potentially leading to unsafe operating conditions. A third incorrect approach that selects modules based on their individual current rating without considering the cumulative current in parallel strings or the voltage in series strings, and then undersizes the OCT, is a direct violation of NEC requirements. This creates a severe fire risk, as the OCT would not adequately protect the conductors from thermal damage during an overcurrent event. The professional decision-making process for similar situations should involve a systematic evaluation of module specifications, VMP, IMP, VOC, ISC, inverter specifications, maximum input voltage, maximum input current, and the applicable NEC requirements. This includes calculating the maximum system voltage under cold conditions, determining the appropriate OCT based on the calculated string current and NEC rules for continuous loads and conductor ampacity, and ensuring all wiring and conduit are sized according to NEC standards. Prioritizing safety and code compliance above all else is the cornerstone of professional practice. Question 8. Process analysis reveals that a solar PV installer is tasked with designing a battery-based system for a residential client. The installer has identified a specific deep-cycle lead-acid battery bank and a solar array with a known maximum power point voltage and current. The installer needs to select a charge controller that will ensure optimal battery health and system safety. Which of the following approaches best aligns with regulatory requirements and professional best practices for this selection? Option A. Opt for a charge controller that is listed for general electrical use but does not specifically mention compatibility with deep-cycle lead-acid batteries or offer adjustable charging profiles, as long as its voltage and current ratings appear sufficient. Option B. Select a charge controller based solely on its ability to handle the solar array's maximum current, and assume that most modern controllers will adequately manage the charging process for lead-acid batteries without needing specific profile adjustments. Option C. Select a charge controller with a current rating exceeding the solar array's maximum output by at least 25%, ensuring it has configurable charging stages that can be set to match the lead-acid battery manufacturer's specifications, and verifying it includes overcharge, overdischarge, and reverse polarity protection features. Option D. Choose the charge controller with the highest voltage rating available, assuming this will provide the most robust charging capability for any battery type, and prioritize models that are advertised as universal without specific compatibility checks. Correct answer is C. Select a charge controller with a current rating exceeding the solar array's maximum output by at least 25%, ensuring it has configurable charging stages that can be set to match the lead-acid battery manufacturer's specifications, and verifying it includes overcharge, overdischarge, and reverse polarity protection features. Explanation. Scenario analysis. This scenario presents a common challenge for solar PV installers, selecting the appropriate charge controller for a battery-based system. The professional challenge lies in ensuring the charge controller not only meets the immediate electrical demands, but also complies with safety standards and optimizes battery longevity, directly impacting system performance and client satisfaction. Misjudging the charge controller's capabilities or features can lead to system underperformance, premature battery failure, or even safety hazards, all of which carry significant financial and reputational risks for the installer. Adherence to the NABCEP exam scope, which emphasizes practical application and regulatory compliance within the U.S. context, is paramount. Correct approach analysis. The correct approach involves selecting a charge controller that explicitly lists compatibility with the specific battery chemistry, e.g., lead-acid, lithium-ion, and offers configurable charging profiles that match the battery manufacturer's recommendations. This ensures the battery receives the correct voltage and current stages, bulk, absorption, float, to maximize its lifespan and capacity. Furthermore, the charge controller must possess integrated system protection features such as overcharge, overdischarge, reverse polarity, and short-circuit protection, as mandated by relevant U.S. electrical codes and standards like the National Electrical Code, NEC, and old listings for safety. Voltage and current ratings of the charge controller must also be appropriately sized to handle the maximum output of the solar array and the charging requirements of the battery bank, preventing damage to the controller and ensuring efficient power transfer. Incorrect approaches analysis. Selecting a charge controller based solely on its maximum current rating without considering battery chemistry or charging profiles is a significant regulatory and ethical failure. This oversight can lead to improper charging, damaging the battery and potentially violating manufacturer warranties and NEC requirements for safe battery operation. Choosing a controller that lacks essential protection features like overcharge or reverse polarity protection directly contravenes safety standards and the NEC, creating a substantial risk of fire or equipment damage. Relying on a controller that is not listed by a recognized testing laboratory, e.g., OL, for the intended application is a critical safety violation and a breach of professional responsibility, as it bypasses essential safety certifications. Opting for controller with a fixed charging profile that does not match the specific battery chemistry ignores the fundamental principles of battery management and can lead to premature battery degradation, failing to meet the expected performance and lifespan, which is a dereliction of professional duty. Professional reasoning. Professionals should approach charge controller selection by first identifying the battery bank's chemistry and capacity, then determining the solar array's maximum voltage and current output. This information dictates the required voltage and current ratings for the charge controller. Subsequently, the installer must verify that the chosen controller supports the specific battery charging algorithm, e.g., multi-stage charging for lead-acid, specific temperature compensation for lithium-ion, and offers the necessary protection features as outlined in the NEC and relevant OL standards. Consulting battery manufacturer datasheets for recommended charging parameters is crucial. This systematic, safety-first, and performance-oriented approach ensures compliance with all applicable regulations and best practices for long-term system reliability. Question 9. Compliance review shows that a client is requesting to install a solar PV system with battery storage, but has expressed concerns about the upfront cost of the battery monitoring system, suggesting a less sophisticated unit that cannot provide detailed state of charge. So C, information or critical alerts. The client also inquired about pushing the depth of discharge, DOD, limits beyond the manufacturer's recommendation to maximize the usable capacity of the battery bank. As a certified solar PV installer, NABCEP, what is the most appropriate course of action? Option A. Explain to the client the critical importance of a robust battery monitoring system for safety and longevity, and the risks associated with exceeding recommended depth of discharge limits, recommending adherence to manufacturer specifications and industry best practices for both. Option B. Inform the client that while a sophisticated monitoring system is ideal, a simpler one will suffice, and that exceeding DOD limits is a common practice to gain more usable energy, proceeding with both requests. Option C. Agree to the client's request for the less sophisticated monitoring system and advise them to manually track battery usage to avoid overdischarge, while also proceeding with exceeding the recommended depth of discharge limits to maximize capacity. Option D. Install the less sophisticated monitoring system and inform the client that while it lacks detailed SOC, they can infer battery status from voltage readings and proceed with exceeding the recommended depth of discharge limits, citing potential cost savings. The correct answer is A. Explain to the client the critical importance of a robust battery monitoring system for safety and longevity, and the risks associated with exceeding recommended depth of discharge limits, recommending adherence to manufacturer specifications and industry best practices for both. Explanation. This scenario presents a professional challenge because it requires the certified solar PV installer to balance client cost-saving desires with critical safety and performance standards mandated by the NABCEP certification and relevant U.S. electrical codes. The installer must exercise sound judgment to avoid compromising the long-term reliability and safety of the energy storage system, even when faced with pressure to reduce upfront expenses. The correct approach involves prioritizing the manufacturer's specifications and established best practices for battery system design, even if it means a higher initial cost. This aligns with the ethical obligation of a NABCEP-certified professional to ensure installations are safe, reliable, and meet all applicable codes and standards. Specifically, adhering to the recommended depth of discharge, DOD limits for the chosen battery chemistry, is crucial for maximizing battery lifespan and preventing premature degradation, which directly impacts the system's performance and the client's long-term investment. Furthermore, ensuring the battery monitoring system is adequately specified to track state of charge, SOC, and other critical parameters is essential for safe operation and proactive maintenance, as required by industry best practices and often implicitly by electrical codes concerning energy storage systems. An incorrect approach would be to accept the client's request to use a less robust battery monitoring system that cannot accurately track SOC or provide critical alerts. This fails to meet the professional standard of ensuring system safety and reliability, potentially leading to overdischarge situations, reduced battery life, and safety hazards. Ethically, it breaches the duty of care owed to the client. Another incorrect approach would be to disregard the manufacturer's recommended duty for the chosen battery type to achieve a higher usable capacity. This directly violates manufacturer guidelines, leading to accelerated battery degradation, voiding warranties, and compromising system performance, all of which are unprofessional and potentially unsafe. It also demonstrates a lack of understanding of battery charging and discharging characteristics and their impact on longevity. The professional decision-making process for similar situations should involve clearly communicating the technical rationale and long-term implications of different battery system configurations to the client. This includes explaining the importance of battery monitoring for safety and performance, and the impact of duty on battery lifespan. If a client insists on a lower-cost option that compromises safety or performance, the installer should document this discussion and the client's decision, and potentially decline the project if it cannot be completed to professional and code-compliant standards. The installer's primary responsibility is to ensure a safe and functional system, even if it requires educating the client on the value of proper components and adherence to best practices. Question 10. Investigation of battery storage system design for new off-grid solar PV installation reveals the client is insistent on using a specific lithium-ion battery chemistry known for its high energy density, but has expressed concerns about its cycle life under deep discharge conditions. As a certified solar PV installer, NABCEP, what is the most professionally responsible approach to designing the battery storage system? Option A. Select a battery chemistry and model that is NRTL certified for energy storage systems, has a manufacturer's warranty that covers the intended depth of discharge and cycle life for an off-grid application, and can be safely integrated according to NEC Article 480 and Article 705, even if it means advising the client against their initially preferred chemistry. Option B. Proceed with the client's preferred lithium-ion battery chemistry due to their insistence, assuming the high energy density will compensate for potential cycle life limitations and focusing primarily on meeting the client's stated preference. Option C. Install the client's preferred battery chemistry, prioritizing its availability and cost-effectiveness, and deferring detailed safety and performance compliance checks to a later stage or assuming the manufacturer's general specifications are sufficient for all off-grid applications. Option D. Design the system based solely on the total energy capacity, kWh, required to meet the client's daily energy needs, without a detailed analysis of the battery's power output, kW, or its suitability for the specific charge/discharge patterns of an off-grid system. The correct answer is A. Select a battery chemistry and model that is NRTL certified for energy storage systems, has a manufacturer's warranty that covers the intended depth of discharge and cycle life for an off-grid application, and can be safely integrated according to NEC Article 480 and Article 705, even if it means advising the client against their initially preferred chemistry. Explanation. This scenario presents a professional challenge because the certified solar PV installer, NABCEP, must balance the client's desire for a specific battery technology with the critical need to ensure the system's safety, reliability, and compliance with applicable U.S. National Electrical Code, NEC standards, specifically Article 705 for interconnection and Article 480 for batteries. The installer must also consider the long-term performance and warranty implications of the chosen battery chemistry in an off-grid or hybrid context, which often involves more demanding charge/discharge cycles than grid-tied systems. The decision requires a deep understanding of battery technologies, their operational characteristics, and their integration into a PV system, all within the framework of U.S. electrical safety regulations. The correct approach involves a thorough technical evaluation of the proposed battery chemistry against the specific demands of the off-grid or hybrid system, considering factors like depth of discharge limits, cycle life, temperature tolerance, and charge/discharge rates. This evaluation must then be cross-referenced with the manufacturer's listed and labeled capabilities and limitations, ensuring they align with the intended application and comply with NEC requirements for battery installations, including ventilation, overcurrent protection, and disconnects. The installer must also verify that the battery is certified by a nationally recognized testing laboratory, NRTL, for its intended use, and that its integration into the PV system adheres to Article 705 guidelines for interconnection, particularly regarding system protection and operational modes. This ensures a safe, code-compliant, and reliable system that meets the client's needs while upholding professional standards. An incorrect approach that prioritizes the client's stated preference for a specific battery chemistry, without a comprehensive technical and regulatory review, fails to uphold the installer's responsibility for safety and compliance. This could lead to a system that is unsafe, underperforms, or violates NEC requirements, potentially resulting in fire hazards, equipment damage, or legal liabilities. Another incorrect approach that focuses solely on the battery's energy capacity, kWh, without considering its power capability, kW, or its suitability for the specific charge/discharge profile of an off-grid or hybrid system, is also professionally unacceptable. This oversight can lead to a system that cannot adequately meet peak load demands or is prematurely degraded due to excessive cycling, compromising system functionality and longevity. A third incorrect approach that overlooks the need for NRTL certification for the battery and its components, or fails to ensure proper integration according to NEC Article 705, introduces significant safety risks. Without proper certification, the equipment may not meet established safety standards, and improper interconnection can lead to dangerous electrical conditions, including arc faults and short circuits. Professional decision-making in such situations requires a systematic process. First, understanding the client's needs and constraints. Second, conducting a thorough technical assessment of available technologies, including their performance characteristics and limitations. Third, rigorously evaluating compliance with all applicable U.S. codes and standards, particularly the NEC. Fourth, consulting manufacturer specifications and certifications. And finally, communicating findings and recommendations clearly to the client, explaining the rationale behind the proposed solution and any limitations of their initial request. Question 11. Benchmark analysis indicates that a residential solar PV installation requires exposed wiring to run from the array's DC disconnect to the inverter located on the exterior wall of the garage. The installer must select a wiring method that ensures long-term durability, safety, and compliance with the National Electrical Code, NEC, for this exposed outdoor environment. Which of the following approaches best meets these requirements? Option A. Leave the conductors completely unprotected and exposed to the elements, relying on their insulation for protection. Option B. Run the conductors using flexible nonmetallic conduit, FNMC, rated for sunlight resistance, but leave the conduit ends unsealed where they enter the disconnect and inverter. Option C. Install the conductors with enlisted, weather-resistant rigid metal conduit RMC or intermediate metal conduit IMC, ensuring all fittings and connections are also listed for outdoor use and properly sealed. Option D. Utilize standard PVC conduit, as it is readily available and easy to bend around corners, and seal the conduit ends with silicone caulk. The correct answer is C. Install the conductors with enlisted, weather-resistant rigid metal conduit RMC or intermediate metal conduit IMC, ensuring all fittings and connections are also listed for outdoor use and properly sealed. Explanation. This scenario presents a professional challenge because it requires the installer to balance aesthetic considerations with critical safety and code compliance requirements for exposed wiring. The choice of conduit and its routing directly impacts the long-term integrity of the electrical system, its resistance to environmental damage, and the safety of occupants and emergency responders. A failure to adhere to the National Electrical Code, NEC, in this situation can lead to system malfunction, fire hazards, and significant liability. The correct approach involves utilizing listed, weather-resistant conduits specifically designed for exposed outdoor applications, such as rigid metal conduit RMC or intermediate metal conduit IMC, and ensuring all connections and fittings are also listed for outdoor use and properly sealed. This method prioritizes the protection of the wiring from UV degradation, moisture ingress, physical damage, and provides a robust grounding path as required by NEC Article 300. The NEC mandates that exposed wiring systems be protected by approved raceways or other approved means to prevent damage and ensure safety. Using listed components and proper installation techniques ensures compliance with NEC 110. 3b, which requires listed equipment to be installed in accordance with listing and labeling instructions. An incorrect approach would be to use non-listed, flexible conduit not rated for outdoor exposure, such as standard PVC conduit or flexible non-metallic conduit. While these might be easier to install, they are not designed to withstand the harsh outdoor environment, leading to premature degradation, potential UV damage, and compromised physical protection. This violates NEC 300. 5, which specifies requirements for underground and exposed raceways and cables, and NEC 300. 10, which mandates that electrical equipment be installed so as to be mechanically protected against contact and damage. Another incorrect approach would be to leave the wiring completely exposed without any form of raceway or protection. This is a direct violation of fundamental NEC principles regarding the protection of conductors and creates an immediate safety hazard, failing to meet the requirements of NEC Article 300. Professionals should approach such situations by first consulting the NEC and local amendments to understand the specific requirements for exposed wiring in the given environment. They should then select materials that are listed and labeled for the intended application and environmental conditions. A systematic installation process that ensures all connections are secure, sealed, and that the conduit provides adequate physical protection is paramount. When in doubt, consulting manufacturer specifications and seeking clarification from the authority having jurisdiction is a crucial part of professional decision-making. Question 12. Compliance review shows a client expresses a strong desire for energy independence, specifically wanting to maintain power during utility outages and reduce their reliance on the grid. They are considering a solar PV system and are asking about options that can provide backup power. What is the most appropriate system configuration to recommend, considering both their stated goals and the need for regulatory compliance in a U.S. jurisdiction? Option A. A grid-tied system with net metering, assuming the utility's net metering policy allows for export of excess generation. Option B. A hybrid system incorporating battery storage, designed to provide backup power during outages while also allowing for grid interconnection and net metering when available. Option C. A purely off-grid system designed to meet 100% of their annual energy consumption, with no connection to the utility grid. Option D. A standard grid-tied system without battery storage, as this is the most common and cost-effective solar PV installation. The correct answer is A. A grid-tied system with net metering, assuming the utility's net metering policy allows for export of excess generation. Explanation. This scenario presents a common challenge for solar PV installers, balancing client desires with regulatory compliance and system feasibility. The professional challenge lies in accurately assessing the client's stated needs against the practical limitations and requirements of different system types, particularly when considering grid-tied versus off-grid configurations and the integration of battery storage. Misinterpreting these needs or misapplying regulatory frameworks can lead to significant financial penalties, system inoperability, and reputational damage. The correct approach involves a thorough assessment of the client's energy consumption patterns, their desired level of energy independence, and the available utility interconnection policies. Specifically, understanding the nuances of net metering agreements, the requirements for grid-tied systems, and the distinct operational and safety standards for off-grid or battery-based systems is paramount. Adhering to the National Electrical Code, NEC, and any applicable state or local utility interconnection standards is non-negotiable. For a client seeking to minimize reliance on the grid and potentially operate during outages, a hybrid system with battery storage, designed to meet specific load requirements and comply with all relevant codes for both grid-tied and off-grid operation, is the most appropriate solution. This approach prioritizes safety, reliability, and regulatory adherence while meeting the client's stated goals. An incorrect approach would be to recommend a purely off-grid system without a comprehensive analysis of the client's actual energy needs and the feasibility of meeting those needs solely through generation and storage. This fails to consider the potential for grid interconnection, which might be more cost-effective or practical for the client, and ignores the specific NEC requirements for off-grid systems, which differ significantly from grid-tied systems. Another incorrect approach would be to propose a standard grid-tied system with net metering without adequately addressing the client's stated desire for energy independence during outages. This would fail to meet the client's core requirement for resilience. Finally, recommending a battery-based system without a clear understanding of the client's load profile and the specific utility interconnection agreement for battery storage could lead to non-compliance with utility requirements or an undersized/oversized system, resulting in suboptimal performance and potential regulatory issues. Professionals should employ a decision-making framework that begins with a detailed client needs assessment, followed by a thorough review of applicable regulations, NEC, State Utility Commission rules, local building codes, and an evaluation of system design options, grid-tied, off-grid, hybrid battery storage. This framework emphasizes understanding the interplay between client goals, technical feasibility, and regulatory compliance to arrive at the most appropriate and compliant system design. Question 13. When evaluating solar photovoltaic modules for a residential installation, which approach best ensures that the selected modules will perform reliably and safely under typical site conditions, considering both manufacturer specifications and relevant industry standards? Option A. Analyze module datasheets for STC and PTC power ratings, temperature coefficients, VOC, ISC, and fill factor, and confirm they meet relevant OL and IEC certifications. Option B. Focus exclusively on the module's fill factor as the primary indicator of its overall performance and efficiency. Option C. Select modules based solely on the lowest cost per watt, assuming all certified modules perform similarly. Option D. Prioritize modules with the highest STC power rating and verify they have OL 1741 certification. Correct answer is D. Prioritize modules with the highest STC power rating and verify they have OL 1741 certification. Explanation: this scenario is professionally challenging because a solar PV installer must ensure that the chosen modules are not only compliant with relevant standards, but also perform optimally under real-world conditions, which can deviate significantly from ideal laboratory settings. The installer has a professional responsibility to the client to select equipment that meets performance expectations and safety requirements, as outlined by NABCEP ethical and technical standards, which implicitly rely on adherence to U.S. regulatory frameworks like those established by OL and the National Electrical Code, NEC. The correct approach involves understanding how module specifications, particularly those defined under Standard Test Conditions, STC, and Photovoltaic Test Conditions, PTC, translate to actual site performance, recognizing that temperature significantly impacts module output, as quantified by temperature coefficients, is crucial. The installer must then consider how these factors, along with the module's inherent electrical characteristics, VOC, ISC, fill factor, will affect the overall system design and energy production. This holistic understanding, grounded in the data provided by certified testing, OL, IC, allows for accurate system sizing and performance prediction, directly aligning with the NABCEP installer's duty to provide reliable and efficient solar installations. This approach prioritizes client benefit and system integrity, adhering to the spirit of professional practice. An incorrect approach would be to solely rely on STC ratings without considering PTC or temperature coefficients. STC represents ideal, laboratory-like conditions that are rarely replicated in the field. Ignoring PTC, which provides a more realistic estimate of power output under typical operating temperatures, leads to an overestimation of energy generation and potentially undersized inverters or other system components. This failure to account for real-world performance deviations can result in a system that does not meet the client's energy needs, violating the professional obligation to deliver a functional and effective installation. Another incorrect approach would be to disregard module testing and certification altogether, assuming all modules perform similarly. OL and IEC certifications are critical indicators of safety and adherence to established performance benchmarks. Failing to verify these certifications means the installer risks using modules that may be substandard, unsafe, or prone to premature failure. This directly contravenes the regulatory expectation for installers to use listed and approved equipment, jeopardizing both system longevity and the safety of the installation, which is a fundamental ethical and legal requirement. A third incorrect approach would be to focus only on the module's fill factor without considering its relationship to VOC and ISK under varying environmental conditions. While fill factor is an important metric for module efficiency, its value is not static and can be influenced by temperature and irradiance. Narrow focus on fill factor in isolation, without understanding how it interacts with other electrical parameters and environmental factors, leads to an incomplete assessment of module performance and potential system design flaws. The professional decision-making process for similar situations should involve a systematic evaluation of all available module data, prioritizing information derived from certified testing and real-world performance indicators. Installers must bridge the gap between theoretical specifications and practical application by understanding the implications of temperature, irradiance, and other environmental factors on module output. This requires a thorough review of datasheets, an understanding of testing methodologies, SDC/VS, PTC, and a commitment to selecting equipment that meets both safety and performance expectations for the specific installation site. Question 14. Quality control measures reveal that a preliminary energy audit for a commercial client, which formed the basis for initial PV system sizing, may have underestimated the building's actual peak demand and daily energy consumption due to outdated equipment information. The client has also indicated potential future upgrades to their HVAC system. What is the most appropriate next step for the certified solar PV installer? Option A. Inform the client that the preliminary audit is sufficient and that any discrepancies are their responsibility to manage. Option B. Immediately recommend a significantly oversized PV system to ensure all potential future loads are covered, regardless of current consumption. Option C. Proceed with the initial PV system sizing based on the preliminary audit, assuming the client's future needs will be met by grid power. Option D. Conduct a more detailed analysis of the building's current and projected load profile, incorporating updated equipment data and considering the impact of proposed HVAC upgrades before finalizing PV system sizing. The correct answer is D. Conduct a more detailed analysis of the building's current and projected load profile, incorporating updated equipment data and considering the impact of proposed HVAC upgrades before finalizing PV system sizing. Explanation. This scenario presents a common implementation challenge where initial assumptions about a client's energy consumption derived from a preliminary energy audit may not accurately reflect their actual usage patterns or future needs. The professional challenge lies in ensuring the PV system is appropriately sized to meet the client's load requirements without oversizing, leading to unnecessary cost and potential underutilization, or undersizing, leading to unmet demand and client dissatisfaction. This requires a nuanced understanding of load profiles, energy efficiency, and the limitations of initial data. The correct approach involves a thorough reevaluation of the load profile and energy efficiency measures before finalizing the PV system design. This includes engaging with the client to understand any planned changes in their operations or equipment that could impact energy consumption, and verifying the effectiveness of recommended energy efficiency upgrades. This aligns with the NABCEP Code of Ethics, which emphasizes competence, honesty, and acting in the best interest of the client. Specifically, it upholds the principle of providing accurate and reliable information and ensuring that the installed system meets the client's needs and expectations, which is paramount for a successful and sustainable PV installation. An incorrect approach would be to proceed with the initial system sizing based solely on the preliminary audit without further verification. This fails to acknowledge the dynamic nature of energy consumption and the potential for inaccuracies in initial assessments. Ethically, this could be seen as a failure to exercise due diligence and could lead to a system that does not adequately serve the client's needs, potentially violating the principle of providing competent and professional services. Another incorrect approach is to immediately recommend a significantly larger system to err on the side of caution. While seemingly addressing potential underestimation, this approach can lead to oversizing, which is financially detrimental to the client and may not be the most efficient use of resources. It bypasses the crucial step of optimizing energy efficiency and accurately forecasting load, which is a core competency for a certified installer. This could be viewed as a lack of professional integrity if the primary driver is to increase system size for profit rather than for genuine need. A third incorrect approach is to dismiss the client's concerns about the preliminary audit and insist on the original sizing. This demonstrates a lack of client engagement and a failure to adapt to new information or potential discrepancies. It disregards the client's perspective and the possibility that the initial assessment might have overlooked critical factors, potentially leading to a breach of trust and a failure to meet the client's actual requirements. The professional decision-making process in such situations should involve a systematic review of all available data, open communication with the client, and a commitment to accurate load forecasting and system sizing. This includes verifying energy audit findings, assessing the impact of proposed energy efficiency measures, and understanding the client's current and future energy needs. The goal is to arrive at a system design that is both technically sound and economically viable for the client, adhering to the highest professional and ethical standards. Question 15. Analysis of a homeowner's request to install solar PV modules with minimal visible racking, flush against the roof surface, to achieve a sleek, integrated appearance, and how this request impacts the installer's adherence to the National Electrical Code, NEC, and best practices for system performance and safety. Option A. Inform the homeowner that the request cannot be met due to aesthetic concerns and recommend a traditional racking system without offering any alternative solutions. Option B. Proceed with the flush installation as requested, assuming that modern modules are designed to withstand higher temperatures and that the aesthetic benefit outweighs minor code deviations. Option C. Explain to the homeowner that while a flush appearance is desired, the NEC requires specific mounting hardware and clearances for module installation to ensure proper ventilation, structural integrity, and fire safety, and propose alternative racking solutions that offer a cleaner look while meeting code. Option D. Prioritize the homeowner's aesthetic preference by installing modules as flush as possible, using custom brackets that minimize visible racking, even if it slightly reduces airflow beneath the modules. The correct answer is D. Prioritize the homeowner's aesthetic preference by installing modules as flush as possible, using custom brackets that minimize visible racking, even if it slightly reduces airflow beneath the modules. Explanation. This scenario presents a professional challenge because a solar PV installer must balance the client's desire for a specific aesthetic with the fundamental requirements of safe and compliant system operation. The installer's primary responsibility is to ensure the system meets all applicable codes and standards, which are designed to protect the public and the property. Compromising on essential safety or performance aspects for purely aesthetic reasons is a direct violation of professional ethics and regulatory mandates. The correct approach involves prioritizing the technical and safety requirements dictated by the National Electrical Code, NEC, and local building codes. This means ensuring proper module spacing, secure mounting, adequate ventilation, and correct electrical connections, even if these elements are not as visually appealing as the client might prefer. The justification for this approach lies in the NEC's mandate to protect life and property from electrical hazards and fire. Adhering to these codes is not optional. It is a legal and ethical obligation for any certified installer. An incorrect approach would be to accede to the client's request for a flush-mounted system without adequate clearance. This failure stems from a disregard for NEC Article 690, which specifies requirements for module mounting and spacing to prevent overheating and ensure structural integrity. Another incorrect approach would be to use non-certified or inappropriate mounting hardware to achieve a sleeker look. This violates NEC requirements for listed and labeled equipment and compromises the system's safety and longevity, potentially leading to structural failure or fire hazards. A third incorrect approach would be to ignore the impact of shading on system performance due to the proposed aesthetic modifications, which, while not a direct code violation in the same vein as safety, represents a failure to deliver a system that functions as intended and meets the client's underlying need for solar energy generation. Professionals should employ a decision-making framework that begins with understanding the client's desires, followed by a thorough assessment of how those desires align with all applicable codes and standards. If there is a conflict, the installer must clearly communicate the code-based limitations to the client, explain the risks associated with noncompliance, and propose alternative solutions that meet both aesthetic preferences and safety requirements. This process emphasizes transparency, education, and adherence to professional and legal obligations. Question 16. System analysis indicates a residential rooftop solar PV installation is planned for a property with an older, potentially less robust roof structure. The chosen racking system is a common rail-based design, Which of the following approaches best ensures compliance with the Certified Solar PV Installer (NABCEP) standards and relevant U.S. regulations for this scenario? Option A. Focus primarily on ensuring all electrical grounding and bonding requirements as per NEC Article 690 are met, as this is the most critical safety aspect for PV systems. Option B. Proceed with installation using standard attachment hardware as per the racking manufacturer's general guidelines, assuming the roof structure can support typical PV system loads without specific structural verification. Option C. Prioritize verifying the racking system's compatibility with the roof type and consulting the manufacturer's specific instructions for attachment methods, while also cross-referencing these with the structural load requirements outlined in the National Electrical Code (NEC) and any applicable local building codes. Option D. Rely on the installer's past experience with similar roof types and racking systems to determine the most efficient and secure mounting method, without needing to re-verify manufacturer specifications or code requirements for this specific project. The correct answer is C. Prioritize verifying the racking system's compatibility with the roof type and consulting the manufacturer's specific instructions for attachment methods, while also cross-referencing these with the structural load requirements outlined in the National Electrical Code (NEC) and any applicable local building codes. Explanation: this scenario is professionally challenging because the installer must balance structural integrity, code compliance, and manufacturer specifications for the racking and mounting system, all while considering site-specific conditions that may not be explicitly detailed in standard documentation. The primary challenge lies in interpreting and applying the National Electrical Code (NEC) and manufacturer's instructions to a unique installation environment, ensuring the system's long-term safety and performance. The correct approach involves a thorough review of the site's structural characteristics, including roof type, material, and load-bearing capacity, in conjunction with the specific racking system's engineering documentation and the relevant NEC requirements for mounting PV systems. This ensures that the chosen mounting method is not only compliant with Code E.g. NEC Article 690, Part VI, which addresses grounding and bonding, and relevant sections on structural mounting, but also adheres to the racking manufacturer's explicit installation guidelines and limitations. This integrated approach guarantees that the system is securely fastened, capable of withstanding environmental loads, wind, snow, and properly bonded for safety, thereby fulfilling the installer's ethical obligation to provide a safe and reliable installation. An incorrect approach that prioritizes speed over thoroughness by only consulting the racking manufacturer's general installation manual without verifying site-specific structural suitability or local building codes is professionally unacceptable. This failure violates the installer's duty to ensure the structural integrity of the installation, potentially leading to system failure, property damage, or injury, and contravenes the spirit and letter of NEC requirements that mandate safe and secure mounting. Another incorrect approach that focuses solely on meeting the minimum requirements of the NEC for electrical connections and grounding, while neglecting the specific structural attachment methods and load ratings detailed by the racking manufacturer, is also professionally flawed. This oversight can result in inadequate structural support, even if the electrical components are code compliant. The NEC implicitly requires that the entire system, including its mounting, be safe and secure. A third incorrect approach that relies on anecdotal experience or the practices of other installers without consulting the specific project's engineering documents, manufacturer's instructions, and current NEC provisions is ethically and professionally irresponsible. This approach disregards the unique requirements of each installation and the potential for evolving code requirements and best practices, leading to non-compliant and potentially unsafe installations. Professionals should employ a decision-making framework that begins with a comprehensive site assessment, followed by a detailed review of all relevant documentation, engineering reports, racking manufacturers' installation manuals, and the applicable sections of the NEC. This framework emphasizes a layered approach to safety and compliance, ensuring that all aspects of the racking and mounting system design and installation are addressed, from structural load capacity to electrical bonding and environmental resilience. Question 17. The monitoring system demonstrates a consistent underperformance in energy generation during periods of moderate to heavy snowfall, despite no apparent issues with the PV modules themselves. The installation occurred on a steep, asphalt shingle roof in a region with significant annual snowfall. The installer utilized a standard flush-mount racking system with direct-to-rafter attachments. Which of the following approaches best addresses the potential underlying cause of this underperformance and ensures long-term structural integrity and code compliance? Option A. Recommend cleaning the PV modules more frequently during snowy periods to remove any accumulated snow, assuming the underperformance is solely due to snow cover on the modules. Option B. Assume the underperformance is an inherent characteristic of PV systems in snowy climates and advise the client to accept the reduced energy output during winter months. Option C. Suggest replacing the existing racking system with a ballasted system, as ballasted systems are generally more effective in snowy conditions, without further assessment of the current roof structure or load calculations. Option D. Investigate the racking system's compatibility with the steep roof pitch and asphalt shingles for snow shedding, and review the attachment method's load transfer to the rafters in relation to the calculated snow loads, ensuring compliance with NEC Article 690 and relevant building codes. Correct answer is D. Investigate the racking system's compatibility with the steep roof pitch and asphalt shingles for snow shedding, and review the attachment method's load transfer to the rafters in relation to the calculated snow loads, ensuring compliance with NEC Article 690 and relevant building codes. Explanation. This scenario presents a professional challenge because it requires the installer to balance multiple, potentially conflicting factors related to structural integrity, code compliance, and long-term system performance. The installer must not only select appropriate racking and attachment methods, but also ensure these choices are compatible with the specific roof type and can withstand environmental loads, all while adhering to the National Electrical Code, NEC, and relevant building codes. Failure to properly assess these elements can lead to structural damage, system failure, safety hazards, and noncompliance, resulting in significant financial and legal repercussions. The correct approach involves a thorough assessment of the roof structure, its material, and its condition, followed by the selection of a racking system and attachment methods that are specifically designed and rated for that roof type, and the anticipated wind and snow loads in the installation location. This selection must be guided by the manufacturer's installation instructions and the requirements of the NEC, particularly Article 690, Solar Photovoltaic Systems, and Article 110, Requirements for Electrical Installations, as well as any applicable local building codes. The installer must verify that the chosen attachment methods will not compromise the roof's structural integrity or its weatherproofing. This systematic, code-driven, and manufacturer-compliant process ensures the safety, durability, and legal compliance of the solar PV installation. An incorrect approach that prioritizes speed or cost over thorough assessment would be to use a generic attachment method without verifying its suitability for the specific roof type and its load-bearing capacity. This fails to comply with the NEC's requirement for installations to be made in a neat and workmanlike manner, and to be mechanically supported and protected from damage. It also likely violates building codes that mandate structural integrity and proper load management. Another incorrect approach would be to select a racking system based solely on its aesthetic appeal or perceived ease of installation, without adequately considering the wind and snow load calculations for the specific site. This neglects the critical safety aspect of ensuring the system can withstand environmental forces, which is a fundamental requirement of both the NEC and building codes. Such an oversight could lead to catastrophic failure of the racking system and the PV array. A third incorrect approach would be to assume that a racking system approved for one roof type is universally suitable for all roof types, without consulting manufacturer specifications or local building codes. This demonstrates a lack of due diligence and a failure to adhere to the principle that installation methods must be appropriate for the specific materials and structural characteristics of the building. This can lead to improper load transfer to the roof structure, compromising its integrity and potentially voiding warranties. The professional decision-making process for similar situations should begin with a comprehensive site assessment, including a detailed inspection of the roof's condition and type. This should be followed by a thorough review of the project's location-specific wind and snow load requirements. Next, consult manufacturer documentation for racking systems and attachment methods to identify products rated for the specific roof type and load conditions. Always cross-reference these selections with the latest editions of the NEC and any applicable local building codes. Document all assessments, selections, and justifications to ensure accountability and provide a clear record of compliance. Question 18. Research into a residential client's energy consumption for a solar PV system design reveals a significant discrepancy between their stated energy usage and the data presented on their utility bills. The client insists they use a substantial amount of electricity due to multiple hydro appliances, but their bills show consistently low kilowatt-hour (kWh) consumption over the past year. As the certified solar PV installer, which approach best aligns with professional standards and regulatory expectations for accurately determining the system's energy load requirements? Option A. Rely on the client's verbal assertion of high energy usage and design a system based on their description of appliance use, assuming the utility bills are inaccurate or do not reflect their true consumption. Option B. Prioritize a system design that maximizes the number of solar panels that can physically fit on the available roof space, assuming the client desires the largest possible system regardless of their actual energy needs. Option C. Conduct a detailed analysis of the client's past 12 months of utility bills to establish a baseline of actual energy consumption, and then engage in a follow-up conversation with the client to understand potential reasons for the discrepancy and discuss future energy needs. Option D. Focus solely on calculating the theoretical maximum instantaneous power draw of all appliances the client mentions, and size the system to meet this peak demand, disregarding the duration and frequency of appliance use. The correct answer is A. Rely on the client's verbal assertion of high energy usage and design a system based on their description of appliance use, assuming the utility bills are inaccurate or do not reflect their true consumption. Explanation. This scenario presents a common challenge for solar PV installers. Accurately assessing a client's energy consumption to design an appropriately sized system. The professional challenge lies in balancing the client's desire for energy independence and cost savings with the practical limitations of available roof space, budget, and the need to comply with relevant codes and standards. Misinterpreting or inadequately assessing load can lead to an undersized system that fails to meet expectations or an oversized system that is cost-prohibitive and potentially inefficient. Careful judgment is required to gather accurate data, understand the client's usage patterns, and apply appropriate methodologies. The correct approach involves a thorough review of historical energy consumption data, typically from utility bills, and a detailed discussion with the client about their current and anticipated future energy needs. This includes understanding appliance usage, potential for energy efficiency upgrades, and any planned changes like electric vehicle adoption or additions to the household. This method aligns with the principles of responsible system design, ensuring the proposed PV system is tailored to the client's actual load profile, which is a fundamental aspect of good engineering practice, and implicitly supported by the need for systems to be safe and effective as per general electrical codes and installer best practices, even if not explicitly detailed in a single NABCEP-specific document for this exact scenario. The goal is to provide a system that meets the client's needs without over- or undersizing, thereby maximizing their return on investment and satisfaction. An incorrect approach that relies solely on a quick visual inspection of the property and a general estimate of appliance usage is professionally unacceptable. This method lacks the data-driven rigor required for accurate load calculation and can lead to significant design errors. It fails to account for seasonal variations in energy use, specific appliance efficiencies, or the cumulative impact of multiple loads, potentially resulting in a system that does not meet the client's energy goals. This approach also risks violating the installer's ethical obligation to provide competent and reliable services. Another incorrect approach that focuses only on the maximum instantaneous power draw of all appliances without considering their actual usage duration and frequency is also flawed. While peak load is a factor in some electrical system design, for PV system sizing, understanding the total energy consumed over a period, kWh, is paramount. This method would likely lead to a gross overestimation of energy needs, resulting in an unnecessarily large and expensive system. This is not only financially imprudent for the client, but also potentially leads to a system that is not optimized for their actual consumption patterns. Finally, an approach that prioritizes installing the largest possible system the client can afford regardless of their actual energy consumption, is ethically questionable and professionally unsound. This sell-up mentality disregards the client's specific needs and budget constraints, potentially leading to a system that is far larger than necessary. This can result in wasted resources, a longer payback period, and a failure to meet the core objective of providing an efficient and cost-effective solar solution. It undermines the trust between the installer and the client and deviates from the professional responsibility to provide solutions that are appropriate and beneficial. Professionals should employ a systematic approach to load calculation. This involves 1. Obtaining and analyzing historical energy consumption data, utility bills. 2. Conducting a detailed client interview to understand current and future usage. 3. Performing a site assessment for available space and shading. And 4. Using this comprehensive data to model energy production and consumption, thereby determining the optimal system size. This data-driven, client-centric methodology ensures accurate sizing, compliance with best practices, and client satisfaction. Question 19. The control framework reveals a residential solar PV installation project where the existing electrical service panel has limited space for additional breakers. The client is concerned about the overall cost of the system and has questioned the necessity of certain safety features beyond basic overcurrent protection. The installer must determine the appropriate level of overcurrent protection, surge protection, ground fault protection, and rapid shutdown implementation in accordance with the National Electrical Code, NEC, for this scenario. Which of the following represents the most professionally responsible and code-compliant approach? Option A. Install only standard overcurrent protection circuit breakers as the primary safety measure, as this is the most cost-effective solution and the existing panel space is limited. Option B. Install appropriately sized circuit breakers for overcurrent protection and consult with the client regarding the feasibility and cost implications of adding rapid shutdown devices, surge protection, and ground fault protection, ensuring all installed components meet NEC requirements. Option C. Install rapid shutdown devices, surge protection, and ground fault protection without explicit client approval, assuming these are universally mandated and the client will accept the added cost. Option D. Install appropriately sized fuses for overcurrent protection and defer the decision on surge protection, ground fault protection, and rapid shutdown to a future upgrade if the client requests it. Correct answer is B. Install appropriately sized circuit breakers for overcurrent protection and consult with the client regarding the feasibility and cost implications of adding rapid shutdown devices, surge protection, and ground fault protection, ensuring all installed components meet NEC requirements. Explanation. This scenario presents a common challenge for solar PV installers, ensuring compliance with evolving safety standards, particularly regarding rapid shutdown, while also considering the practicalities of existing electrical infrastructure and client budget. The professional challenge lies in balancing the imperative of life safety, mandated by the National Electrical Code, NEC, in the U.S., with the economic realities of a project. A thorough understanding of the NEC's requirements for rapid shutdown, overcurrent protection, surge protection, and ground fault protection is crucial to avoid compromising safety or exceeding project scope without proper client consultation. The correct approach involves a comprehensive site assessment to determine the specific rapid shutdown requirements based on the system's configuration, location, and intended use, as dictated by the NEC. This includes identifying all necessary components for overcurrent protection fuses or circuit breakers sized appropriately, surge protection devices, SPD, to safeguard equipment from transient voltage events, and ground fault protection systems to prevent electrical shock hazards. Crucially, it necessitates a clear communication with the client about these requirements, their rationale, and any associated costs, ensuring informed consent and adherence to the NEC's intent for firefighter safety and emergency responder access. An incorrect approach would be to assume that standard overcurrent protection alone is sufficient, neglecting the specific mandates for rapid shutdown systems. This failure directly contravenes NEC Article 690.12, which outlines requirements for reducing shock hazards during emergencies. Another incorrect approach is to omit surge protection devices, leaving the PV system vulnerable to damage from lightning strikes or other transient overvoltages, which, while not directly a rapid shutdown failure, is a critical aspect of system protection often addressed concurrently. Furthermore, neglecting to implement appropriate ground fault protection, as required by NEC 690. 5. Creates a significant safety hazard by failing to detect and interrupt ground faults, increasing the risk of electrocution. Professional decision-making in such situations requires a systematic process. First, thoroughly review the applicable NEC sections relevant to the project's scope and location. Second, conduct a detailed site assessment to identify all potential hazards and system requirements. Third, develop a compliant design that addresses overcurrent protection, surge protection, ground fault protection, and rapid shutdown. Fourth, communicate all findings, recommendations, and associated costs transparently to the client, obtaining their approval before proceeding. Finally, ensure all installations are performed according to the approved design and relevant codes, with proper documentation. Question 20. Comparative studies suggest that the effectiveness of a solar PV system is heavily influenced by site-specific conditions. A certified solar PV installer, NABCEP, is tasked with designing a rooftop solar PV system for a residential property. The installer has access to basic roof pitch and orientation data and is aware of the general requirements for structural load capacity and electrical code compliance. However, they have not yet performed a detailed site-specific analysis of potential obstructions or the precise solar irradiance available throughout the year, which approach best aligns with the professional responsibilities and regulatory framework for a NABCEP-certified installer in this jurisdiction. Option A. Focus primarily on ensuring the system meets the minimum structural load requirements and electrical code compliance, as these are the most critical aspects for permitting and safety. Option B. Prioritize maximizing the roof orientation and tilt to capture the most direct sunlight, assuming that any minor shading can be mitigated by inverter technology and that permitting will be straightforward if the system is structurally sound. Option C. Proceed with system design based on the available roof pitch and orientation, assuming standard structural and electrical code compliance, and then submit plans for permitting. Option D. Conduct a comprehensive site assessment including a detailed shading analysis using appropriate tools, a solar resource assessment, and a structural evaluation, ensuring all findings are integrated with local building codes and permitting requirements before finalizing the design. The correct answer is C. Proceed with system design based on the available roof pitch and orientation, assuming standard structural and electrical code compliance, and then submit plans for permitting. Explanation. This scenario is professionally challenging because it requires the installer to balance competing priorities, maximizing energy production, ensuring structural integrity, adhering to local building codes, and obtaining necessary permits. The installer must not only understand the technical aspects of solar PV, but also navigate the regulatory landscape specific to the certified solar PV installer, NABCEP, exam jurisdiction, which implies adherence to U.S. federal, state, and local regulations. A failure in any of these areas can lead to project delays, safety hazards, or legal repercussions. The correct approach involves a comprehensive site assessment that integrates shading analysis, solar resource assessment, and structural considerations, all within the framework of local building codes and permitting requirements. This approach is correct because it prioritizes safety and compliance, which are paramount in the solar industry and are explicitly addressed by NABCEP standards and U.S. building codes. By conducting a thorough shading analysis using appropriate tools, assessing the solar resource, and evaluating structural capacity, the installer ensures the system is not only efficient but also safe and legally installed. This proactive integration of all factors, including local codes and permitting, minimizes risks and ensures long-term system performance and owner satisfaction, aligning with ethical installation practices and regulatory mandates. An incorrect approach that prioritizes only maximizing roof orientation and tilt without a detailed shading analysis is professionally unacceptable. This failure stems from neglecting a critical factor that significantly impacts energy production and can lead to underperformance, potentially violating contractual obligations or misrepresenting system capabilities. Furthermore, it bypasses a key step in ensuring the system's effectiveness, which is a core competency expected of a certified installer. Another incorrect approach that focuses solely on structural considerations and local building codes, while overlooking solar resource assessment and shading analysis, is also professionally flawed. While structural integrity and code compliance are vital, neglecting the solar resource and shading analysis means the system may be structurally sound and code compliant, but ultimately inefficient and unable to meet the owner's energy generation expectations. This oversight can lead to client dissatisfaction and a failure to deliver on the primary purpose of a solar PV installation. Finally, an approach that solely relies on permitting requirements without a thorough site-specific analysis of shading, solar resource, and structural integrity is fundamentally misguided. Permitting is a procedural step that verifies compliance with existing codes and regulations. It does not replace the installer's responsibility to perform a detailed technical assessment. This approach risks obtaining a permit for a system that is technically unsound, inefficient, or unsafe, leading to potential failures and liabilities. The professional decision-making process for similar situations should involve a systematic, multifaceted approach. First, conduct a thorough site assessment, including detailed shading analysis using appropriate tools and techniques, and a realistic solar resource assessment. Second, evaluate structural capacity and compatibility with the proposed system. Third, meticulously research and apply all relevant local building codes and regulations. Fourth, proactively engage with the permitting authority to understand and fulfill all requirements. Finally, integrate all findings to design a system that is safe, code compliant, structurally sound, and optimized for energy production, ensuring all aspects are documented and communicated to the client.